The basic problem we saw is that developers are too smart. Besides that, they're also too expensive. So we have to make sure that they don't have to do stupid administrative tasks. I mean, everybody knows it. If you have a developer orders a new keyboard and he has to fill out an Excel form, you get a mad developer. And so we should automate things. That's what we generally do when working in software. So for example, we stopped, as a software engineering field, we stopped doing manual releases and instead figured that we should have declarative components describing how our DOM should look like without doing the actual manipulations ourselves. And so we figured that we should do the same for data flow. We should use transparent reactive programming that makes sure that data is updated at the proper places. So today I first will talk a bit about MobX and the philosophy behind it. And after that I will show how observable data is actually a more powerful method than immutable data. So MobX is a transparent reactive programming library, and I'll show you in a minute what that entails. And its main goal is to make state management more simple, but also more scalable. And those two goals don't conflict. So basically the idea behind MobX is if you have some data, some state, a person describing me, and you probably want to render that somewhere in the DOM, in the browser. So what you do is you write a component. This is a React stateless function component, which basically takes a person and renders its name. And then you use React, for example, to render it into the DOM tree. The problem, of course, arises when you start changing the data. So if you just look at this code, what you probably intend is that when you change the name of this person, we want to have that name reflected in the DOM. It's in 99% of the cases obvious that that should happen. So why should we care how that is done? And also, if you change the age of that same person, then the DOM shouldn't be updated, because if that would happen and you would have a large application, it would be way too slow. So that's basically what MobX does. You can mark data as this data is observable. It can be derived into something else. Please check it for me. And you can mark a component as observer, which basically means whenever there's relevant data being changed, please re-render it in the DOM. And that's basically it. If you run this code in a fiddle, then you will see that the name inside your DOM will update whenever you change the name, and that it won't re-render if you change the age of the person. And probably you have heard this equation about React. Your view is a function of your state. And actually, I don't really agree with that equation. And the reason for that is simple. If it's just a function, then you still have the responsibility of calling that function. A function in itself is useless as long as it isn't called. So actually, I would say that the view is a transformation of your state. It's just your state, but represented in a different way. And actually, what we want is that it's a live transformation of our state, not a transformation what happens whenever we feel comfortable to invoke it, because we might forget about cases, but it should just always reflect what our state is. It should automatically transform our state into a view. And that is basically what the MobX autorun function does. It takes a function, and it runs this function again whenever some data that is used inside this function has been changed. So if the state changes, then the view is updated. So that means that the consistency of your UI is always guaranteed, whenever, regardless how it is changed or when it is changed. So having asynchronous processes is MobX no fundamentally different from having synchronous process. You don't have to do any special tricks for that. It's just a change of the state in the future. But we know it will react. So the basic flow of data in MobX is that there's a central state which captures all your state of your application. And it should be as small as possible because many things can just be derived from a state, like caches, like the DOM. Those are all just computed values. So from the state, their computed values are derived, and also side effects might be triggered. For example, if you change some data, a network request might need to be made. And so whenever there's an action influencing your state, we know that everything that comes after the state will be consistent. So there are four essential functions in the API of MobX. And one is observable. And it's a function that, or a decorator that takes objects or arrays or primitive values and just make sure that MobX is able to track what happens to these pieces of data. And there's autorun, you just saw it. And related to autorun is observer, which basically puts a React component in an autorun function. So it reruns whenever relevant data is changed. Computed values are very similar. They also take an expression and re-evaluate it when needed. But there's one smart thing about computed values, is that because it's a value and not a side effect, we know when it's needed and when it is not. So if there's a computed value, which is used by nobody, MobX will make sure it's never evaluated. So actually it achieves lazy evaluation. And finally are actions, and those are an optional concept, but they are used to make clear where you intend to change your state. And MobX can optimize around that. So this is what we use MobX for at Mendix. This is an application development studio, and you can drag and widget and change them. They have all properties. So you can build forms and pages. But what's actually more interesting is that we also have a designer in which you can design your database. So these are basically database tables. These are the cross associations. And what we make sure is that whenever we drag things around, then for example, you see the arrows moving around. And actually, we didn't do anything special for that. Basically, MobX just makes sure for us that that is kept consistent. And I'll show you how that works in a simplified version. So here we have the very essence of that same editor, a lot more simplified, but it's powered by exactly the same mechanisms. It doesn't have less or more optimizations or something. The principles are exactly the same. And so what this looks behind the scenes. So what we have here is a sample, very simple JSON JavaScript structure that describes our state. So we have an array of boxes. This is my font. And we have an array of arrows. And for boxes, we use classes. But for arrows, we just use plain JavaScript objects, just to show that you can use both. So actually, what is interesting is that these arrows, again, have direct references to the boxes we have. They don't use normalization, they don't store strings, they just reference to the boxes. So what we effectively have is a graph of data, because the arrows connect to the boxes, and they're part of the same store. And actually, so far, this application doesn't do anything yet. It has some components. For example, here's a component that renders a box. It has a div with the coordinates. And when you drag it, it will update the properties of the box. But it doesn't do anything yet because React doesn't take care of that itself. It takes care for local state, but not for data you pass into components in general. So what we basically need to do is to bring this application alive, to make it reactive. And so to do that, we just as I said earlier, we have to make sure our state is observable. So this makes the state observable, and if you have boxes, then you can instead use decorators for that. So by default, MobX will make plain JavaScript objects in their entirety observable. But if you use classes, then you have fine-grained control over which attributes you want to be observable. And with actually is a property that can be derived from another piece of state, namely the name. So that one we mark as computed. And if you run that, then actually still nothing will happen except the sidebar. Apparently the sidebar is observing our state. But the components cannot be dragged yet. But what's interesting is that we actually didn't do anything with our state yet. We kept it in the same shape. The actions weren't changed. They still are straightforward as they were before. And so what we can do now is that we can mark our components as observer. So for example, the canvas component maps over the arrows and maps over the boxes. And observer makes sure that whenever something relevant changes to those collections, it will re-render. So basically, it's a full replacement of the concept of should component update and those kind of things. Because it just means that the components can be derived from the state. So what we can now do is that we can now drag this thing along. And the interesting thing is that the arrow stays connected. And we actually, in this view, we never explicitly mentioned that this arrow depends on the box. But MobX knows that it depends on the box because we're using the from box of the arrow. And from that box, we use its x coordinate. So it knows that these values need to be tracked. Actually, you can see that by investigating the component, and it will tell you which pieces of data were relevant for the rendering of this component. And so these exact pieces of data will be observed. So this is a very fine-grained, very optimized way of making sure that the proper pieces of state are used for the rendering and trigger an update. And actually what is nice to look at that was a misclick. So I want this arrow. And we see now that this arrow depends on the from and the to property of the arrow we passed into it. And its x and y coordinates of the two boxes related to it. Now this is what MobX has determined for us. So what's interesting to see what happens if we change. So now the arrows, if you see them, they're connected to the left of the box, not to the middle. That's a bit ugly, so we can easily change that by, for example, using the, no, not that one. Simultaneous programming, it's a new achievement unlocked. So now we started using the width of those boxes in our rendering, which we didn't before. So if you now start to drag this box around, you see it's now attached to the middle. And if you inspect its dependencies again, if I can manage to click that one pixel, there. We see now that it also depends on the width and the name of the box. And actually, it doesn't depend on the other box, so apparently I used the wrong one. Okay, I had to use better styling. Anyway, you get a clue. But what is funny is now, if you look, I've made this too hard for myself. Did somebody bring a mouse? Okay, so it depends on the width. And what you actually see is that because the width is a computed value, it's not a value on its own, but it's again a value that depends on another value, namely the name of the box, because the width is just the name multiplied by a constant. So what actually is happening now is that something you might as a developer very easily forget, but if you now change the name of this box, you see that the arrow will move to the right. Because it has traced this dependency tree, and we're now changing the name, and MobX knows that the name is relevant for the width, and that's relevant for the rendering of the arrow. And so these are usually this kind of edge cases you easily forget as a programmer. And then when you finally think about it, then you have to go to the feature in your code that changes the name of the box and make sure that if the box has changed, arrows are re-rendered, which is a completely unrelated other feature. So this means that you would increase the amount of work you have to do each time you add a feature, because suddenly the name becomes relevant for the rendering of the arrow, which wasn't before, just because you wanted to use proper coordinates. So what MobX stands for is that state is the only truth, and that actions and derivations, those things are all decoupled. So actions modify some state, but they don't care of what needs to happen beyond that. And then if the state is changed, MobX takes care that the proper derivations are run for you, instead of you having to trigger the proper repaints yourself. So why that is very relevant for us at Mendix, that's because of our architecture. So at Mendix we have these very complicated models. You just saw a piece of it with forms and data models describing what an application looks like, because we built an application to build applications. So we have a large collection of classes, roughly 500, describing all the different concepts that exist in an application, like input boxes, events, microflows, web service integrations. So we have, for that, we have a public SDK describing all the things that exist. And then on the bottom, we have two IDEs we are building. One is a modeler which only runs on the desktop, so we call it a desktop modeler. It's a C# thing. And the other is a web-based web modeler built using React. And so both those modelers, they operate on the same models of applications. And for each different model, there are separate editors. So you saw just an editor in which we can edit pages, and you saw an editor in which we can edit the data model. And those two editors are maintained by different teams. But those editors have influence on each other, because if I change the data model, then that has impact on the bindings of the input widgets to some entry in the database, for example. So what MobX allows us to do is that we can ignore the fact that those things are related, and all of the teams just talk in terms of the state. So any editor is free to update whatever state it wants. We don't we don't have to tell to each other which kind of actions we fire or something. No, every editor is just free to change the state. And we know for sure that from that state, any other editor is updated if it's using that state. But we don't have to know that because it's tracked for us. So that means that separate teams can individually work on separate features and separate packages, and we still know that everything that uses this data is synchronized. So we don't have to need to coordinate the actions between the different teams. We don't need to coordinate with each other about which pieces of data we're using. The only thing we need to know is what is the shape of the data we have, which classes exist, which attributes do they have. So, and one example where that is very relevant are validation rules. So when is a MobX function, and it just tracks the first function, and whenever that evaluates it true, it executes the second one. And so we have here a function that checks if the speed of a car exceeds the speed limit, and if that happens, then a fine will be sent. So that's basically a side effect will be triggered. Now what's interesting is that it doesn't matter where or when the speed or the speed limit of those concepts is changed, but if it's changed and this equation returns true, we know for sure that the fine will be sent. That's the guarantee MobX gives us. So what our actually rules in our system look like is always a bit like this. They walk over the complete data tree and they check all settings of properties and check if there are no double names and if the correct database type is selected and if the type of the attribute in the database matches the input widget type. It's one big mess. There are hundreds and hundreds of these rules. And so we cannot possibly track ourselves when which rule needs to be fired. But the cool thing is that we don't have to. We know that the correct rules are fired if an important piece of data that influences that rule is changed. And we know that the other rules won't be fired. And so these rules are always visible, and all the editors have influence on when these rules are run. But the rules are maintained by, again, a separate team, and they don't care when somebody else changes the data. So that is generally what MobX does in its essence. And if you want to look through this in more detail, just take an Egghead course. It's free, takes you half an hour, and then you have seen all the essential concepts of MobX. And I started making this open source about roughly a year ago. And in the meantime, it has grown significantly. It got over 5,000 stars on GitHub, which I'm quite proud of, especially because it's not backed by Facebook or something. And it's also got into the top 1% downloaded packages on NPM. And what amazed me the most was that it turned out to be the second most popular state management library in the recent JavaScript survey. And it's also nice to know that it's not just used in the React world, but also with other frameworks. And people react quite differently to MobX. So what I hear the most is that it's so simple and fast. And it's quite common for people which convert to MobX that they end up with PRs that throw away 30% of their code, which is quite funny. Other people complain that it's a bit magic, it's all happening behind the scenes, it's all done for you. You can't really control it or step through it, or at least you shouldn't want to. But that's the price in principle we pay for abstractions. It's the same what we do with React. We don't care how the virtual DOM works. We just understand its conceptual thing, what it does for us. But we don't actually debug or try to understand that code. And especially when they will be introducing fibers, it will be even more impossible. So yeah, that's some magic, but the idea is that the semantics should be clear, and that is why you should be able to trust it. And the nice thing about MobX is that it's quite opinionated on how you structure your data. You can use a tree, you can use a graph, you can use plain objects, you can use classes. It doesn't care, basically. It's just data and things that derive from data, and how the data is shaped doesn't matter. On the other hand, people are, for the same reason, sometimes sad, because it doesn't tell them how to build applications. It just takes care of some data flow for them. But there's no, this is what your file should look like, these are the proper file names, please use these folders. It's just opinionated about that. And some people are happy that it uses mutable data, because that's straightforward to work with. It matches very closely to the mental model we humans have of the world. It's how we think about things. But on the other hand, people are sad because it doesn't use immutable data. Because immutable data has all these nice mathematical properties. So another question to answer is, should you use immutable or mutable data? Especially in the React world, that's quite a question. Or you could also say, should you use Redux or MobX? Or maybe an even better question, Elsa or Anna? You might be wondering how that relates, but the basic point is I have two small daughters, so this is a question I get the most. They're always arguing over who should play who. So let's talk a bit about Anna. Anna is a very well-controlled, very predictable, very well-behaving girl. On the other hand, there's the previous one was Elsa, sorry. I'm confusing it. On the other hand, there's Anna, and she's very agile and very straight to the point, and she just hates ceremony. And of course, that totally doesn't relate to my talk, so I hope you have read what was on the slides. So, which approach is better? Basically, I think I cannot tell you, or at least I cannot give an unopinionated, neutral point of view opinion about that. But I think the relevance of the benefits of either mutable data or immutable data depends per project. The way of each benefit is different. And although those things are quite opposite, so what may be more interesting is to take a look at what are the driving principles behind those approaches to state management. So Redux is all about predictability. It's called predictable state container. And how does it get its predictability? By providing transactional state. And transactional state means that at any moment in time, you just have your state, you can look at it, it's immutable, it will not change, and then some action happens, and then you have a new state. You can always differ between those two, and you can see the action that have been applied to get from one state to the other. And outside of those actions, nothing can happen or should happen to your state. So that makes it predictable. The word transaction already mentions that. It's like a bank account. MobX, on the other hand, tries to get simplicity by making sure that your state is as small as possible, and as many things as possible are derived from your state, so that there's no redundancy and those kind of things. So what's actually interesting is that the philosophies of those two concepts are in principle not conflicting. So that's brought me to the quest for a snapshotable state, which is replayable, so that you can have transactions, while still having the convenience of MobX actions which are straightforward and which don't require you to reproduce a whole new world whenever you try to change the tiniest bit. So that's a bit like trying to combine two different directions. So let's go back to my demo. Let's find it. Oh yeah, this is one. So we had this demo, and what is nice about it is that it already supports time traveling. So it can go back and forward in time. That was me being lost. So, but that was the MobX demo, so how can it be replayable? How can it have time traveling when it's not transactional? Well, actually, it's quite simple. What it does is it just serializes the state so that you have a snapshot, basically a deep clone of the state, and it pushes that on a collection of states. So you have a history of states. And of course, that needs to happen when something changes, every time something changes. But that is easy in MobX. We can just put auto-run around it. So now we make sure that whenever some data, which is used by the serialization function, is changed, a new snapshot will be produced and will be put on the array. And that's how we can do time traveling. So basically, that is because a snapshot is just another transformation of the state. You just transform it into some JSON tree structure. There are some problems with this approach, though. It's a bit limited. And one of the problems is that because MobX is unopinionated, it doesn't know how to serialize your state. If you use just a tree as state without classes, it's easy to serialize and to deserialize. But if you use classes, classes don't have a concept in JSON, so it cannot deduct from your JSON which class it should instantiate. So for that, the serializer package was introduced. It makes it more simple. But there are more problems. Deep serializing your state is very expensive because you need, if you have a large state, you need to walk your entire tree, make a complete copy of that. And it's not only expensive CPU-wise, it's always also expensive memory-wise because you will be filling up memory like crazy by copying your state each time something is changed. So it lacks structural sharing. But these problems can all be solved. That's a nice thing. So what you can do is that you can constrain ourselves to trees, because trees are easy to serialize. And we also know that snapshots are just derived values. And MobX is very good at deriving value. And we even know that we can solve the structural sharing problem, because basically rendering a DOM is also a structural sharing problem. If we change some data, we want the correct components to update, and we want the other components to be left alone. So that's also structural sharing, but just in another form. So apparently these are solvable problems. And to show you how this can be solved quite easily, I'm going to take first a bit deeper dive into computed values. You already saw them. So here you have a plain JavaScript class, and it has a full name getter property. So each time you inspect the full name property of this object, it will evaluate, and there's something nasty in it because it will return an array. So each time you evaluate this function, you'll get a fresh array. That's a bad thing. So if you change the first name and then you inspect the full name, it will say calculating, and if you inspect it another time, it will reevaluate, give you a new array, and it will tell you another time it is calculating. But actually, if you have observable data sources and reactive derivations, there's inversion of control. So because data is no longer pulled through your system, but pushed through your system, it's actually runtime behavior is different. So if you have now two observable attributes and the computed full name, then what will happen if we change the first name, that will trigger the computed value to be rerun. It needs to be derived again because the backing data changed. But after that, if we print it twice, it doesn't need to re-evaluate because it knows that it can reuse its previous answer because there was no data changed in the meantime. So actually, here you have structural sharing in the most minimal form. Both those log statements will print exactly the same array. It's just an effect of inversion of control. So if you apply that concept to, for example, a to-do class, you could give it just a computed value representing the JSON structure, which returns a simple plain object representing the to-do. The nice thing is that this function will always return the same object unless something did actually change in that to-do item. And if you have then a to-do store with a collection of to-dos, then you can just map over the to-dos if you try to get its JSON representation. And for any to-do that was not changed, it will just reuse the same JSON representation. So what happens if I modify a property over here, a new snapshot, a new JSON representation will be generated. That will trigger the computed value and the boxes collection to be updated. So it will run the map again, but the map will reuse the old snapshots of the other to-dos. Oh, wrong slide, it should be to-dos. Anyway, the point is clear. And so on and so on. So you get structural sharing for free if you use computed values to serialize your state. So that's actually something very cool, I think. So based on that idea, I recently published an experimental package. It's still much work in progress, but it's based on those ideas. And it's, this time, opinionated, so it tells you how to structure your stores. But as in return, you get things like time traveling and structural sharing. And so its core concept is that your state is a tree of models. And those models can be mutable, they can be rich, they can be observable, they can have actions, have computed values. But for every model, there's always a snapshot which is immutable and which represents the state of the model at that moment in time. And those snapshots uses structural sharing. And to create a model, there's the concept of factories. And a factory just gets an example model, and every time you invoke the factory, it makes a copy of the example you gave it. And so basically, it's effectively, it just creates a new observable object based on a copy of the example model, and mixes in any snapshot you provide to it. So if you had some previous snapshots, some previous state, it will make sure that that state is represented in the new instance you get. So a box factory just look like this. It has 3 attributes, those will be made observable, and a computed value. And then we can create a new box by just providing a complete or a partial snapshot. And for the store, the same. There we can use the map of and the array of modifiers so that MobX state tree knows what the shape of this object is and how to serialize it. And the selection this time is no longer a reference like it was previously, it's now a string. Because if it was a reference, then we would get a graph, and then it would be hard to infer how it wouldn't need to be serialized. So it's opinionated, but also a little bit more, you have a little bit more boilerplate than MobX. And we have to see whether that's worth the effort or not. So let's talk about those snapshots again. So basically, there are 3 functions to work with snapshots. You can pass a model to the getSnapshot function, and then you get the snapshot at that moment in time. And you can also apply a snapshot back to an existing model instance. And what's even funnier, you can also subscribe to every time a new snapshot is available. And with that, you can build very easily time traveling while having the benefits of structural sharing and not doing expensive computations. So say we have some store, we can just listen to new snapshots coming in, push it on some array, and then we can easily apply a snapshot back to the existing store if we want to play back or forward. You can also do many other things once you have snapshots. For example, if you have a form, but you want to make changes in that form to some object, but you don't want it that it immediately becomes the truth. You want that state just localized in the edit form until you submit it. So what you can then do is you can just clone the to-do, pass it to the form, and whenever the form is submitted, take the snapshot of the clone to-do and apply it back to its original. And actually clone is just invoking the factory of the model with the snapshot of the model. Then you get a new copy of the exact same instance. And with that you can also make testing very easy, because you can just clone some base data, invoke some actions on it, and then check whether the snapshot represents the correct state. So if we mark it as completed, it should be true. And it also integrates very nicely with Jest. I don't know who has used Jest before, but it's pretty awesome. You can just say, I expect the snapshot to match the recorded snapshot. And then if you change some data, it will give an error, this assertion has failed. And then you should either fix your implementation, or you can just say, this is now the correct snapshot, this change is correct, please store a snapshot for me. And it's really awesome to work with. I can recommend it. Not only for state, but also for testing React components. But there's more we can do. So you just saw this application, but actually there are more of them. And what will be interesting is to sync this application with the other one, which turns out to be very easily once we have snapshots. So what we can do is that whenever we have a new snapshot, we can send it over a socket. I'll try it. And once we receive data over the socket, we can just apply the snapshot back to our existing store. Yeah, that looks okay. So if I now start dragging it, you see on the bottom right all the snapshots of the state being synced over the WebSocket, and those two are kept completely in sync. So that's because we have a way to serialize our state very easily. But there's more. The nice thing about observable data, in contrast to immutable data, is that you know exactly what has been changed inside the data. You don't get a new copy of the complete world, where the only thing you know is that this is the new world, but you can actually see, because it's fine-grained observable, what is actually changed. So the MobX state tree package also supports JSON patches out of the box, which is a standard to synchronize changes of JSON. And for that, it provides two functions: onPatch, which is triggered each time a patch is emitted, and applyPatch. So this is very similar to snapshots, except that it just syncs patches. And patches are, of course, way nicer to synchronize. Because if you have a large state tree, these objects which are synced become really, really large, and I wouldn't do that in production. So it's better instead to listen to patches. So if there's a patch, then we want to send a patch to the other side. And if we receive a patch, we just want to apply the patch. So if I now drag, you see there are only very small objects sent along, regardless how big our state has thrown. It's just saying, please replace in this path in the state tree the x value with this new value. That's what JSON patches do. So this you can use effectively to integrate with a backend of some sort. And actually, a nice thing about MobX state tree, because it's a tree, it's actually a fractal structure. So it's a tree consisting of trees consisting of trees. So what you could do is not just register a patch listener on the root of the tree, but you could attach a patch listener at any point in the tree. And so then something very funny happens. So I've now attached two listeners to the tree, one to the root and one to a specific box in the tree. And then I start moving one of those, then I start moving that box. Then I get two patches emitted by each listener emits one patch. And they emit with the correct path relatively to the position they were attached. To put it in a picture, if I change something here, it emits a patch over here with this relative path, but also over there. and describing relatively to that point where in the state tree it changed, and etc., etc. So actually, you see it's a recursive structure. Okay, onto actions. You saw that we were just moving actions, moving boxes by invoking a function. So that doesn't look replayable at all. And we said we want replayable actions to be able to have transactional state. So what MobX state tree does is it reverses the responsibility of the developer. So if you use the Redux, then you have to provide a serialized version of your action, a plain object describing what should happen. But MobX state tree does the inverse. You just invoke a function, and it gives you the description of your action. Because some developers like me are lazy. So an action in MobX state tree is just like this. It's just a function. We mark it as action. And it can just change that instance of the box. So if you move it, we just update the coordinate. And we don't have to reproduce a new world, a new state here. We can just change this localized object. And so we can then just invoke that box and move it around. But for actions, there are two functions. So we can just listen to the fact that an action was invoked. And we can say, please apply this action back to this object. So we can replay it. And that looks roughly like this. On action is very similar to the previous ones, except it can be used as middleware, so it receives a next function. And so here we have basically a middleware on the store that prints what action is invoked. So if we then move a box in the store, then it prints, hey, on this path, this and this method was invoked with these arguments in serialized form. So what you can then do, of course, you should know the drill right now, is that whenever there's an action, and we get some data and the next function in the middleware chain, we can send that description over the wire. We can invoke the next layer in the middleware. And if we receive a message, we can just apply the action to our store. So if we now move the box, there are no patches emitted, but descriptions of the action. So we now see that we first moved the box and then we changed the selection, apparently. So that's just to demonstrate that actions are replayable. And you can also do that for forms. Suppose you have a form and an environment where there's collaboration happening. Then you can just clone the object and apply the snapshot back, because in the meantime, somebody else might also have changed the same object. Like if you have Google Docs or something like that. So a smarter thing to do is then clone the object.
You have 2 minutes left.
How many? Oh, I'm going to talk very quickly. And then apply it back. Actually, you don't, in the end, turns out you don't really have to have a tree as well to do all these things. You can even do this with graphs. But I'm going to leave that as exercise for home, because I have an article demo. So far we have a state tree which is snapshotable and which has replayable actions. Yeah, all ticks checked. So it's the best of two worlds. But there's one more demo. Last one, I promised. No, not the last one. Last but one. So here's to do MVC, the Redux to do MVC. You might have seen it before. And so here are the Redux dev tools. Yeah. So you can change it and then you can replay it back, etc., etc. You might have seen this before. This is just basic Redux stuff. Actually, the fun thing is that this is not entirely a Redux application. It has Redux actions and uses a Redux dispatcher It uses Redux components, it uses Redux DevTools, but it doesn't have a Redux store. And it doesn't have any reducers. And still it's replayable. And that's because it uses MobX state tree behind the scenes. And I'd be, how is that possible? Well, turns out, because we have transactional state, we can just mimic a Redux store with a state tree. So what we just do is that we have a simple function that takes a MobX state tree based store and returns a Redux store, and then passes it down to the Redux provider component, and then everything keeps working as is. And the fun thing is that as Redux store function is as simple as this. GetState is basically synonym for get the current snapshot of the state. And dispatch is basically, please replay this action on my state tree. And similar, subscribing to the next version of the world is basically subscribing to the next snapshot. So, and then our store looks more like this, which is, I think, a lot more straightforward. Don't get confused with this uppercase thing. That's because we want to preserve the old Redux name actions. And because we have that, it also works the other way around. So I here have my Redux DevTools again, but now with our original demo. And you see that even in this entire MobX-based application, it doesn't have any Redux in it, the Redux DevTools still work, because it's just, Redux is just a subset of this mechanism. So, just try it out. I hope this was interesting to see this happening. But what's even more important to remember than just this package is that you saw that a transactional state is just one reactive transformation away. Reactive transformations are actually a very powerful concept. It's like if you have normal function applications, which are very static, which you need to invoke manually, and then you have, like, you enter the era of movies and things are actually reacting. So, try the Egghead course, play with this package, and thanks for your attention.